Hello students. So, today in this session we are going to see that one of the area of thermal properties of matter, that is expansion of liquids. In the last session already we did about the thermometry and expansion of solids. Now, the continuation to that is expansion of liquids, right. So, you all know that I gave all the fundamentals at this moment here, and you know what is the major difference between the solids and liquids. Solids have a defined shape and defined size, defined volume, defined length and defined area, and therefore, length, area and volume expansions, the three types of expansions that we can expect in case of solids. Now, coming to the point of liquids, you know very important one is no defined length. So, depends upon the vessel capacity and we can say that, right, and the second one is a no defined area, but there is a defined volume. You take that 1 liter of water in any kind of the vessel and it always occupy the same one like liter of volume, right. So, therefore, there is a defined volume for the liquids. And another important point is here, liquids cannot be heated directly. Solids can be directly heated, liquids cannot be heated directly. Liquids to be heated by means of the vessels. So, definitely the vessels made up of metals mostly, and definitely the expansion of vessel also to be considered to study about the expansion, actual expansion of the liquids, right. So, now in this case, first of all we will see that here, and what are the different kind of the parameters and all. First we will discuss in this case, like I am going to give that some important fundamentals, and I choose that some questions which are very important, which are related with the previous NEET questions. What are the questions that are covered in the earlier in the different years, and based on that some questions we have choose, and that questions I am going to discuss, right. 1 or 2 questions for your work also I am giving here, you please try after this session, right. Now, coming to the point here, as I already mentioned, liquids have a defined volume, but if you see that here, this is a vessel. Now, you have taken that a liquid up to this, a certain volume of the liquid. Now, up to the level A, when you are heating, so you can definitely expect that here the solid vessel first exposed to the heat, due to which what happens, started expanding. Because of the expansion of the vessel, the liquid level falls to the level B. We feel that a liquid get contracted, it is not that. So, really the liquid level falls from A to B because of expansion of vessel. If you can measure that whatever the volume that come down here, that itself is the volume expansion of the vessel. Now, still if you supply the heat energy, slowly that heat energy enter into the liquid. Now, liquid start expanding. So, naturally what happens here, most of the times, most of the liquids, liquid expansion will be more than expansion of solids. Therefore, it go to the level C. So, you observe children clearly, no confusion. The first we have taken that liquid at A, because of the expansion of the vessel and liquid level appears to fall to the B. Now, really the liquid is located at B. Now, slowly liquid expanded from B to C. So, therefore, we can say that here B to C is the real expansion, and earlier we are under impression that liquid was at A. Now, finally, we observe that liquid is at C. So, therefore, we observe that here the liquid expansion we observe, this is called the observed expansion. Observed expansion, this is called the expansion of vessel, expansion of vessel, volume expansion of vessel, because solid is a, vessel is a solid, therefore, liquid, you may think that here linear and aerial, no, it is a volume expansion of the vessel. Now, let us take that here, this is equal to real expansion of liquid, real expansion of the liquid. So, with this we can clearly say that here real expansion of the liquid is equal to expansion of the vessel plus expansion of observed expansion. Observed expansion can also be called as apparent expansion. So, the simple point here, I will repeat, the liquid is taken at a level A because of the expansion of the vessel, and the liquid level appears to fall to the point B. Still, if you supply the heat energy, the liquid expand up to the C. So, really the liquid expanded from B to C, but we are under impression that liquid expanded from A to C, that is called observed expansion or apparent expansion. This is one of the important one. If you can really remember this, and many questions you can easily solve. right. Now, based on that we have a certain relations and all we will discuss. Now, like expansion of solids, there are two kinds of expansions. First one is a real expansion, other one is apparent expansion here, and real expansion coefficient also will be there here, coefficient of real expansion and the coefficient of volume, I mean apparent expansion here. These are the two different kind of expansions in case of liquids. I told you already, basically there is only one expansion, volume expansion, but volume cannot be measured, that real expansion of the volume cannot be measured. Therefore, first of all what we are getting in the sense like real expansion we are getting, and the next one is apparent expansion. From these two mathematically we can calculate exact the expansion of the liquids, right. Now, we will go to the next. Here, what is the expansion, like a relation between the coefficients of expansions here? You can see just now I mentioned here real is equal to, this is a what actually real expansion, coefficient of real expansion. This is called the apparent expansion, coefficient of apparent expansion, and this is called the expansion of vessel. Normally we take it as glass vessels, that is the reason I mentioned that glass. Otherwise, if at all any other metal is given, accordingly you can take that here. This is called the volume, coefficient of volume expansion of, coefficient of volume expansion of vessel. I took that glass, right. So, gamma r is equal to gamma a plus gamma g. This is a one important point, and based on that many questions we have here, right. Now, we will see that we all know that in the expansion of already solids we discuss volume expansion of a vessel which is a glass or a solid 3 times to alpha. Gamma a is equal to, from this you see gamma r is equal to gamma a plus gamma g, but most of the questions we use this formula for gamma a. Gamma a is equal to gamma r minus gamma g. Children, you please, very very important point to be remember here, for a given liquid, for a given liquid. So, the next we have a question based on my statement at this moment. I will repeat once again, for a given liquid, irrespective of kind of the vessel, irrespective of the kind of the vessel, irrespective of nature of material of the vessel, gamma r is always constant for a given liquid. For example, you take a mercury in aluminum vessel, same mercury you are taking that copper vessel, same mercury you are taken in the glass vessel, you heat it all the three through the same rise of temperatures. So, you find that here real expansion of all these three cases is same, because liquid is the same, but apparent expansion is not same. Apparent expansion depends upon the expansion of the liquid plus expansion of the vessel, right. So, that is the one important point here. Will the real expansion depends upon the expansion of the vessel? No. Real expansion is actual expansion of the liquids, and apparent expansion totally depends upon the expansion of the vessel. Now, here only you can mathematically clearly observe that if at all you are choosing one material which has not having any kind of expansion property, let us take that gamma g is equal to 0. In that case, observed expansion is equal to real expansion, that is it. Okay. Now, and I gave some of the points here. If gamma g is positive, see gamma g is positive here, this is positive, gamma a is less than that of gamma r, gamma g is equal to gamma r, you see gamma g is equal to gamma r, these two gets cancelled, no observed expansion. For example, for this I will tell you, for this point I am giving here, this is a vessel, you have taken the liquid up to this, if the vessel expands, liquid level falls to the B, now the liquid expand to the point C. So, you observe that here, and again liquid come back to the same thing, no observed expansion, right. In that case gamma a is equal to 0, if gamma g is equal to gamma r and the liquid level remains constant. So, that means what you can write? You can also write here gamma a is equal to 0 for this, right, and gamma g is negative. Mathematically you see gamma g already is negative, 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 positive. So, in that case, and you can observe that here if gamma g is negative, the liquid level increases from the beginning. Is it clear? If gamma g is positive, gamma g is greater than that of gamma r, liquid level falls. The same from mathematically you can observe that, right. So, this is about the fundamentals of expansion of liquids, right. And next more two fundamentals are there. First of all, we will see some of the numericals based on this concept. See and apparent expansion of the liquid, you see coefficient of apparent expansion of the liquids, and taken in the two different vessels. In copper vessel is the coefficient of apparent expansion is C, and when it is heated in silver vessel, it is S. Point to be noted, this is a C, coefficient of apparent expansion C, in a copper vessel is C, and in silver vessel is S. If A is the linear coefficient of linear expansion of copper, what is the coefficient of linear expansion of the silver is asking. Children, I already mentioned very clearly, when vessel changes, liquid is the same thing, therefore real expansion is same thing, right. Now I will take that here, real expansion in the first case is equal to, in the first case instance, first vessel which is the copper, real expansion in the second case. What is the formula for the real expansion? Gamma A in the first case, first is the, I am taking that copper, and the gamma vessel, the first case which is the copper, gamma A in the second case plus gamma V in the second case. Now gamma A in the first case is gamma A, apparent expansion, coefficient of apparent expansion C, plus, and gamma in the first case here you see of volume, I mean of a vessel, in the sense you can see coefficient of apparent expansion of the copper is given as A, that is coefficient of apparent expansion, you see that here A is a linear coefficient of expansion, in that case we say that here 3A is equal to gamma A2, gamma A2 is equal to, it is a S, that is apparent coefficient in the silver vessel, plus 3 alpha in silver is asking that only, that is all. Now you can do this calculation, exactly you are going to get that answer, this one you can check that here, C plus 3A minus S by 3 is equal to alpha S, just observe. So, it is one of the important model, and even in place of C, A, S and all other things, some numerical values also will be given and you can substitute. This is not the formula to memorize, the only thing is this is a concept that you need to give a mind, right. Next, now similar question here, very simple, gamma A of the liquid, gamma A of the liquid, gamma A of the liquid is equal to 7 by 8 of gamma R, and gamma G is asking. For this gamma G, you see the options here, and options are asked in terms of gamma R, therefore you have to eliminate gamma A. So, you children, you see that here, you know gamma R is equal to formula, basic formula I am writing, gamma A plus 3 alpha G I am writing, because we require alpha G, and gamma R to be there, gamma A to be eliminated, because options are given in gamma R. So, therefore, you see that here in this case gamma A you can take it, gamma R is equal to 7 by 8 gamma R plus 3 alpha G, and this comes to this side, gamma R minus 7 by 8 which is equal to 1 by 8 gamma R is equal to 3 alpha G. Children, you observe the calculations, alpha G is equal to 1 by 24 gamma R. Okay. So, this is the third option. So, these are the questions which are similar to that of a previous NEET questions, and focus more on this. Now, I will go to the next one. Say this one is the same model, you can try for your practice, I think you can easily understand, similar for your practice I gave this question, and this one is also similar. Okay, one question I will do that here. See, coefficient of real expansion of the liquid 5 times to the linear expansion of the material, that is real expansion. First you write the information is equal to 5 times 2 alpha. You see that here whether is asking alpha or in the confusion, normally we are under impression that gamma will be given. So, it is the alpha of material, alpha of solid, I am taking the glass. Ratio of coefficient of apparent expansion and the real expansion is asking. The simple one here, coefficient of apparent expansion by coefficient of real expansion is asking that, you just observe that here, and do not come to the conclusion by seeing the question I did not cover earlier. First read the question and small information will be there and small substitution will be there, accordingly we can follow that. See, gamma A by gamma R, here given that gamma R and here the gamma A, is asking the relation gamma A and gamma R relation, and how to find out, you can check that here clearly. In this case, see that here gamma A is equal to gamma R minus gamma G we know, and gamma R, because this is given in terms of gamma R here, we can take that here gamma R you can substitute, gamma R is equal to 5 alpha G minus this is 3 alpha G, because you know gamma is equal to 3 alpha. I will write it, gamma is equal to 3 alpha of G. Glass is nothing but, I am not saying that is only the glass, any vessel we are taking the symbol as glass itself, and gamma R is equal to 5 times 2, this one here we can see 2 by 5. So, the answer will be 2:5. Okay, children. So, these are the majorly one formula based calculations. Now, we will go to the next one. See, and remember, this is another important model, and of course, appears to be little tougher side. You just observe that here a vessel of volume V contains two liquids A and B. Density of A is D and its volume is only V by 2, whereas other half of the vessel is filled with another liquid of density 0.8 D, and system is heated to 10 degrees Celsius. Then mass of the liquid mass of the liquid expelled. You observe here, children, observe that calculations clearly. This is a vessel, and up to the half of this one liquid, and up to the next half is this, and you observe clearly which liquid is at the bottom, which liquid is at the top is important here. A is of more denser liquid at bottom here, this is a density D, this density is equal to 0.8 D, and this volume is equal to V by 2, this volume is equal to V by 2. Children, you observe here, and expansion coefficients of expansion of liquid A and liquid B. Coefficients of expansion of liquid A and liquid B, in the sense they are the real expansions only. Observed expansions, unless it is mentioned, we should not count that. Okay, like these are what actually here in this. Now, you please see that here how that whenever you are heating here, then what happens, and liquid start expanding. In that case, what happens here, the liquid started to overflow, and which liquid has a more probability to go out, in the sense only the upper liquid. So, how much of the liquid, see that here the total volume expansion is equal to volume expansion of first liquid and volume expansion of the second liquid. For example, the total together the liquid expansion is equal to say something like a 20 cc. It is not that here, and this also 10 cc, this also 10 cc expands, that depends upon the nature of the liquid and the coefficients. So, but together, and how much of the liquid overflow, the expelled liquid, the volume of the liquid expelled is equal to the total volume expansion of the given liquid. So, for that you can see the total volume expansion you want to find out here, delta V1, that is volume expansion of this liquid. And how to find out the volume expansion of this liquid? I gave you formula, volume expansion of anything is equal to gamma into its volume into delta T. Here it is increased by how much of the temperature? 10 degrees. Now, you can observe, children, what I am taking first gamma 1, which liquid? This is a liquid A, and there is a liquid B here. Gamma A I am taking 12 into 10 power minus 5 into volume is V by 2, original volume is V by 2, and delta T is 10 degrees. Similarly, and delta V2, what is that here? 10 into 10 power minus 5 into volume V by 2 into the temperature increases 10 degrees Celsius. Children, you observe that here, and what exactly calculation? V by 2 into 10, V by 2 into 10 is the same thing, 12, and this is a 10, which is equal to 22 into 10 power minus 5 into V by 2 into 10. Clearly observe that here 11 V, because here the 10 is there, 10 power minus 4. This is equal to the volume increase, the total increase in volume. What we require to know that here in this case he is asking here what is the mass of the liquid comes out. This is the volume of the liquid comes out. We need to find out the mass of the liquid coming out. mass of the liquid coming out is equal to, mass is equal to volume into density, volume of the liquid expelled into the density. Yes, which density to be taken? Is it the density of mixture? No. Which liquid is has a probability to go out? 0.8, 0.8 into D. Delta V is equal to how much? You can substitute here, 11 V into 10 power minus 4 into 0.8 D, which is equal to, you can see the calculations here, the first option will be the correct answer, 8.8 into 10 power minus 4 into V into D. Children, this is one important one, right. I hope you understand this. Now, we will go to the next concept here. Here, this is another formula to find out coefficient of apparent, only formula based topic. Just to remember, there is a which technique is called the specific gravity bottle. What is a specific gravity bottle? In sense, a bottle with a round bottom, a long neck, this one, it is filled the liquid up to this extent, and in this case what happens here, the original mass of the liquid is equal to m. When you heat it, just a simple formula based topic, do not give much mind to this, and it is not that much of the important here. M is the mass of the liquid in this, and x is the amount of the liquid expelled. Now, directly we can tell that here gamma A is equal to x by, what is x here? Volume of the liquid expelled, volume of the liquid expelled. I think I gave that completely. Mass of the liquid expelled is equal to CM, x is equal to mass of the liquid expelled, mass of liquid expelled, and here mass of the liquid original minus mass of the liquid expelled, this is nothing but the mass of the liquid remaining into rise of temperature. That is all the simple calculation here, and that is all about one part of the liquids. Now, the next one here, and same concept that is there in the solids also. In the last session I mentioned clearly, and the same volume of empty space. Children, once you observe that here, and simple diagram, if you understand that, you can easily get that here, and see, this is a one vessel. Now, you are taken that liquid is up to this extent, this is a liquid, this is a volume of empty space, volume of empty space. As a volume of empty space, you all know that here liquid expand, vessel also expand, but it is possible, the volume of empty space remains constant provided volume expansion of the vessel and volume expansion of the liquid is same, for which the volume expansion is same in the sense, what is the meaning of that here? Delta V of the vessel is equal to delta V of the like a liquid. Delta V of the vessel, you can see gamma of vessel, volume of vessel into delta T is equal to volume of gamma of the liquid and the volume of the liquid into delta T. So, delta T is the same. The next formula it is this. See, and the volume of the vessel, gamma of the vessel, volume of the liquid, gamma of the liquid. Gamma of the liquid is real expansion, and the volume of this one, and this is a gamma of the liquid. So, the simple one here, it is possible volume of empty space remains constant provided V1 gamma 1 is equal to V2 gamma 2, or V of liquid gamma of liquid is equal to V of vessel gamma of the vessel. Okay, children, I hope you understand this. Now, I am giving a simple question here based on this, and this is a one important fundamental. Normally, you can take that. See, expansion of mercury is 7 times that of the glass. If the glass vessel is filled 1/7 of its volume, because see, as it is a 7 times, because it is inversely proportional, you can clearly understand that here, if at all the glass vessel is filled up to 1/7 and the volume of empty space remains constant, I will give you a diagram here. See, and you take that here, there is a vessel, this is a liquid mercury, and the total volume is equal to V. This volume is equal to V by 7. then what happens here, if it is a mercury, and definitely the volume of the empty space remains constant in case of mercury, because and clearly mentioned that here expansion coefficient of mercury is 7 times to that of this, then the volume of empty space remains constant, and this is also based on that question. You can try this, right. Now it is only for your practice, this is a previous NEET model only, you can check that your PYQs. Now I will go to the next one. See, variation of density, same in the solids also we have the similar formula, variation of density with the temperature, variation of the density of the liquid with the temperature, the same thing as the volume is inversely proportional to this is a formula, density at T degree Celsius is equal to density at 0 degree Celsius by 1 plus gamma RT, right. So all this formula different ways we can write it here, and this also we can use it. See that here, what is the purpose of this one here, to find out the gamma R, provided density at one temperature, density at other temperatures given. Then what is this, sir, in the sense like density at 0 degree Celsius specifically mentioned, density at T degree Celsius to find out this, okay. And that is all about variation of density, and this is based on that concept here. Just I will check that another problem, I will do that, this is a direct formula, you can see that normally it is a common problem, this one is a previous NEET question. Next I am going to the next question, you see that here similar concept. Next you see that density of the liquid at 100 degree Celsius, that is density at 100 degree Celsius is given, which is equal to 8 gram per cc. Density at 0 degree Celsius given, density symbol can be taken rho also, 8.4 gram per cc. You observe children, and the density as the temperature increases, the density increasing or decreasing, you can observe that here. Density from 0 degree Celsius to 100 degree Celsius, what happens, the density decreases. In case of water it will be different. In the next session, I mean next the topics we are going to see that is called the anomalous expansion of water. First we are seeing that a normal liquid and density at 0 degree Celsius, this is at 100 degree Celsius, direct formula at 0 degree Celsius, and coefficient of cubical expansion of liquid. Which coefficient of cubical? This is a real. For this formula I gave you already, d at a temperature T is equal to density at 0 by 1 plus gamma R into T. We require gamma R, 1 plus gamma R into T is equal to d0 by dt. d0 is equal to how much? 8.4 by 8. Now gamma R into T, temperature is increased by how much? 100 minus 0, 100, which is equal to 8.4 minus 8, you can see that here, minus 1, 0.4 by 8, 0.4 by 8. So children, you can see that next step, gamma R is equal to 0.4 by 8 is equal to, you can clearly see that here 4 by 80, 4 by 80 is equal to 1 by 20, 1 by 20 into 100, this 100 also goes to that side, gamma R is equal to 1 by 2000 per degree Celsius, and which is equal to 5 into 10 power minus 4, you can say that 5 into 10 power minus 4 per degree Celsius. So this is a one simple problem based on the density, variation of density, one of the important one but simple. So most expected question in the solids and liquids, variation of density with temperatures. Next, yeah, this is also similar. What is the fractional change in density? And just I am giving the clue for this. Fractional change in the density in the sense change in density, dt minus d0 by d0 is asking. And for this you can substitute clearly. You observe that value of coefficient of apparent expansion of liquid is given, like a real expansion of liquid is given. Fractional change in density of glycerin when the temperature increase of what actually 40 degrees Celsius, then in its temperature, and what is this here we need to answer. Fractional change in density dt minus d0, dt is equal to, you know that here, and what is the formula you can substitute clearly. I am writing dt is approximately equal to, dt can also be written as 1 minus gamma delta T minus d0 by d0. You take the d0 common and gets cancelled, this d0 0, you can see that here with cancellation here, you can observe that clearly, and in that case gamma t will be there here, gamma t. So, once it is a gamma t, you can calculate how much it is a fractional change, okay, and here the density decreases, therefore, it is a minus you are getting. You substitute the gamma value and T is equal to 40 degrees Celsius and 5 into 10 power minus 4 into 40, and which is equal to, here you are going to get that answer, fourth option, 5 into 10 power minus 4 into 40. You are going to get that this one answer, which is equal to 20 into 10 power minus 3. Children, right. Now, this is also variation of density with temperature, how the density and all, and the 2 questions we did and 2 questions for your work, and you can try immediately after watching this video. Now, we will go to the next one, and apparent weight of the solid immersed. This is one of the important application about the mechanical properties of the fluids as well as expansion of liquids, right. And first of all, from the mechanical properties of fluids, we know the formula here. What is the formula here, and what is the buoyant force? Buoyant force is equal to, what is that? And buoyant force insists whenever the body is placed, and the body loses its weight when completely immersed, and that is only, what is the apparent weight? Apparent weight is nothing but, you can see here, when a body is immersed in liquid, its weight decreases. The apparent weight of the body is equal to V into D minus S into G. What is the D? D is the density of the solid, and S is the density of the liquid I mentioned, and V is the volume of the solid, right. So, this is equal to apparent weight. Apparent weight, we can say that here, apparent weight is equal to, real weight is equal to mg, that you know. Similarly, apparent weight is equal to V into density of the body minus density of liquid into G. This we can also remember here, right. So, from that we can calculate how and all that, because once the density changes, naturally that apparent weight changes, right, and we are going to do one problem, that is the formula for this. And next, D1 and D2 are the density of the liquids at T1 degree Celsius, at T2 degree Celsius, and the volume of the solid at T1 and T2 degree Celsius respectively, V1 and V2. And what is upthrust? What is the formula for the upthrust? Upthrust can also be called as buoyant force. Upthrust is equal to, F is equal to volume of the body immersed, density of liquid, please remember, into T. This is what actually the buoyant force. And you observe clearly, what is that here I just mentioned here, you see, F1 is the buoyant force at temperature T1, F2 is the buoyant force at T2. From that, how to calculate here? F1 by F2 is equal, because you know buoyant force depends upon density of the liquid, assuming that this is constant, assuming that G is constant. If at all the expansion of the body which is placed in the liquid is ignored, then it only depends upon the density of the liquid, here. So, density of the liquid varies with the temperature, you know, according to the buoyant force also changes. Now, buoyant force in the first temperature at second temperature is equal to 1 plus gamma S into T2 minus T1 by T2 minus T1 in this one, and you can substitute that here, F2 is equal to F1 into this. Okay. Now, going to the next one, this is a formula to be remember, right. We have a one question, later we will see that. Next, here, fraction of the body immersed. Compared to the last, this is the most important point here. And what is the fraction of the body immersed? For example, you take that a vessel with a liquid. In this, if at all you take that a liquid of this one here, a body is placed, and assume that is a floating body. And when do you expect that the body to float? If the density of the body is less than that of density of liquid, it will float. And how much of the float, how much will be inside and how much will be outside, depends upon both the densities. And how much of the fraction, whether 1/4 is immersed or 1/3 is immersed or half is immersed, depends upon both the densities, not that only the density of the body. I will repeat once again, no confusion. Earlier I mentioned buoyant force depends upon only the density of the liquid. Buoyant force depends upon density of liquid, no confusions. Whereas, and the fraction of the body immersed, this is the volume of the body immersed, this is the total volume of the body. So, children, you observe that here, what is the fraction? Fraction of the body immersed, fraction immersed. F is equal to volume of the body immersed by the volume of the entire body. For this, what you can write here, we have one formula from the mechanical properties of fluids. In that session you are going to see that here, and Vi by V is equal to how much it is. In that case we have a formula, density of the body by density of the liquid, the fraction of the body immersed. Now from this we can write it as, directly we can say, assuming that if the body is not, if density of the body is not changing, if the rho b is constant, normally we expect that here liquid expansions will be more than expansion of solids. Assume that the body which is placed inside the liquid is not expanding one, only the liquid expands. Because of that, density of the liquid only changes. Now coming to the point here, how the fraction depends upon this, and fraction is inversely proportional to density of the liquid, right. So now you can see in this case, fraction of the body second temperature by the fraction of the body at first temperature is equal to density of the liquid, real expansion of the liquid at the first temperature by at second temperature. For this, from these two you can calculate that the next formula, how to find out the gamma here. We can find out gamma of the liquid is equal to here, and F2 minus F1 by F1 T2 minus F2 T1. This is a formula, a derived formula here, not required at this moment, and this formula you can remember, gamma of the liquid. How to calculate? I will repeat once again. Remember, you know gamma of the liquid almost constant, density varies, and what is the gamma of the liquid, how to calculate, in the sense you can see. First, at one temperature how much of the fraction is immersed. Now increase the temperature, the fraction immersed changes, either may increase or decrease, and fraction the second temperature is F2, fraction at the first temperature is F1, F2 minus F1 by F1 T2 minus F2 T1. This is an important formula here, you just remember. Okay. So this is the one you have to memorize, you can understand that here. Okay. Now from this concept only you will get it here, just substitution only, rho R1, rho R2, and at a different temperatures you can substitute and you are going to get it. Okay children, we will go to the next. Here just now I gave you already, based on that concept. Which concept here? This concept. How much of the fraction is immersed at second temperature, first temperature, F1 T2 minus F2 T1, based on this formula. Just you note that point formula. Now you can see, a solid body floats in a liquid at 20 degrees Celsius, 75% is immersed. 75% is immersed. 75%. That means 3/4 of volume is immersed at 20 degrees Celsius. Now when the liquid is heated to 100 degrees Celsius, at 100 degrees Celsius, and same solid, that means solid expansion is ignored here, same solid floats with 80% is immersed. You note down here why 80% fraction of the body immersed increases, because the density of the liquid decreases. When the density of the liquid decreases, buoyant force decreases. When the buoyant force decreases, what happens here? And the body goes down. If the buoyant force is more, it will push up. When the density, repeat, temperature increase, density decreases. When the density decreases, density of the liquid decreases. Because of that, what happens here? And buoyant force decreases. As the buoyant force decreases and upthrust decreases here, and due to which what happens, liquid goes down, and that is the reason the fraction immersed is increased from 75 to 80, right. Now 75 to 80 here. Now what is that fraction immersed, which is equal to 80%. 80% is equal to 4/5 of total volume. Only 1/5 is outside, 20% is inside, outside, and here 25% is outside at 100 degrees Celsius. Children, then the direct formula here, coefficient of expansion of the liquid is asking. Clearly observe that here, volume expansion of solid to be constant. In this case, just now I gave formula, gamma is equal to fraction immersed in second case, first case, by F1 T2 minus F2 T1. So F2 is equal to this, you can take that here, and fraction only, no, this is a volume, no need to count that here, directly 3/4 only the fraction, and this is a fraction 4/5, and this is equal to F1, this is equal to F2, and T2 is equal to how much it is, 100 degrees Celsius, and T1 is equal to 20 degrees Celsius. You can substitute that here, and gamma is equal to first answer that you are going to get it, 8.33 into 10 power minus 4 per degree Celsius, right children. Now, we will go to the next small concept is there before ending the session. Yeah, the last concept of the expansion of liquids, anomalous expansion of water. Very small concept and very important concept here. All the liquids, I gave that complete theory, just you go through that here, and all the liquids expand on heating, contract on cooling, but a water has a particular behavior between 0 to 4, and you see that here what happens here, and one small graphical procedure you see that here, volume with the temperature start from the 0 degree Celsius. You take the water at 0 degree Celsius. As the temperature increases, the volume of the liquid, what happens here? Decreases, then increases. All other liquids, what happens here? As the temperature increases, go on increasing. How that you see? Other liquids, these other liquids, almost not exactly the linear graph, other liquids is this, and this is pure water. Pure water, what happens here? First, as the temperature increases up to 4 degree Celsius, its volume will be decreasing. Then after that, what happens here? And the volume increases with increase in temperature, like ordinary liquids, other liquids, right. So, this particular behavior is said to be the anomalous expansion of water. And what are the advantages of anomalous expansion of water? I clearly mentioned once you go through that. Okay. Now, and as the volume of this liquid first decreases, water decreases, then increases, and if you see the density graph, density variation with the temperature, density with the temperature, and all the liquids, what happens here? Go on, their density decreases, but the water, what happens? Density increases, then decreases. At 4 degree Celsius, and water occupies the minimum volume, this water occupies the minimum volume, water occupies minimum volume at what temperature? 4 degree Celsius, and it attains maximum density at 4 degree Celsius, right. So, this particular behavior is said to be the anomalous expansion of water. I will repeat, this is one of the important question you find. You have a water at 4 degree Celsius, that is one of the important question you see in any material, in our material also many times it is asked in the exam also. If at all water at 4 degree Celsius, as temperature increases, what happens? Density increase or decrease? You can observe that clearly. As temperature is increased from 4 degree Celsius, density decreases. As temperature decrease, also the density decreases. I will repeat, from 4 degree Celsius, if you increase the temperature, density decrease only for a water. Even if you decrease the temperature, density decreases according to the volume reverse. At 4 degree Celsius, it minimum. If you increase the temperature, volume increases. If you decrease the temperature, volume decreases. So, this is a one important one here, and we can say that anomalous expansion of water. I clearly mentioned that, and what is the advantage of this in the animals which are living in the under the water. This kind of anomalous expansion of water, how much is helpful for them to survive. Okay. Now, you can see the theory point on the last one, and the same points are mentioned clearly. As the temperature of the water increase from 0 to just now mentioned, the apparent weight of the body decreases because the density decreases. Now, in this case, and at 4 degree Celsius, apparent weight of the body is minimum, and further heating, the apparent weight of the body increases. So, all other remaining points are mentioned. These are some of the theoretical points, you please go through that. Children, and expansion of liquids, these are only essential points, and see that once again the formulae and whatever the important all kinds of the numericals I mentioned, right. So, definitely it may be helpful to do that your exams very well, right.